Hey, welcome back to Gold's Garage. So, lots to tell you about. This is the second video on Al Rader's 454 LS7. What the heck is an LS7? I didn't know myself, so we'll get to that. The first video we just did the teardown and discovery. I now have the block back from the machine shop and the heads back from the machine shop, and we're going to try and show you as much detail as possible on this entire build. I have a parts list display. I have the calculations we did. I had Bill Little help me with to determine cranking pressure and pressure ratio. All the things you need to do to measure to make sure that calculation is accurate and correct. And we're going to go through all that. We're going to actually CC a combustion chamber for you on camera, so you can see how that goes if you've never seen that before. Check the deck height on the block. All these things are necessary, and we'll list the things you need to know in order to determine your static compression ratio, your dynamic compression ratio, and your cranking pressure. And so we're also working on a video about project management, and I'm going to jumping around a little bit here. I'm going to show you just quickly. Ali's going to come in here. We're just going to show you quickly part of it. If you take a look at this graph, and it's real important because managing the project is as big a job as doing the work and assembling the engine. So this is a graph, and this is time, and this is cost on this side. Okay, so the conception. Project definition starts off, project definition, you have to start off what you want to do. So we're going to try and build a 454 LS7 to be pump gas friendly, have good street manners, and still make 600 horsepower for a reasonable price. And that, I say reasonable because we're not going to cheap out on important things, but we're not going to waste our money on frivolous gingerbread that you get sucked into by marketing. So then the decision and discovery and planning. So all that took place, tearing the engine down, figuring out what's going on with the engine. Procurement, that's acquiring the necessary parts. And you'll notice I don't even start procurement until we have all the discovery and planning done. I haven't ordered any parts. We're just going to order them now. The construction, the assembly of the engine, commissioning and startup, and evaluation. So if you look at the graph, here it is, opportunity to save. So at the beginning, when you're in this phase, if you change your mind, you find a better way or whatever, you can do that, and it's going to cost you, you're going to save a lot of money, and it's not going to be hard to do. As you progress to the end, your opportunity to save is gone, because if you make changes down here, it's going to be very expensive. So the other part of the graph, kind of a mirror of it, the cost to change. So initially when you're at this stage and you change your mind, you want more compression or bigger cam or more power, or you want to go to a different level, you can do that because it's just changing some entries, on a page. As you go, it gets harder and harder. So it's kind of the analogy that I use. If you're building a house and you get it almost all built and you decide you want the kitchen to be 1 foot bigger, it's going to be very expensive, and you're not going to have any opportunity to save. You're going to be spending. So that's from my project management days, my corporate days, and we're going to incorporate that into a future video. So just a little background. When I was graduating college a long time ago, I had a passion for engines then, just like I still do. And so my dream job would have been working for General Motors Engineering, doing that. And I actually did apply, but they didn't hire me. So, but I still have that passion for engines. And so the other thing I mentioned before, the guys that did design these engines were pretty darn smart, and you better be careful if you're going to try and outsmart them. We're not trying to outsmart them, but things have changed since these engines were designed. The application is different than it was then. The fuel is different than it was then, and a whole bunch of other things. So we're not trying to outsmart them, but we're basically redesigning the engine. And basically what this is, a process of redesigning the engine. We're going to show you all the calculations. I had Bill Little do some major calculation for us. We're targeting about 10.5 to 1 compression ratio and about 185 psi of cranking pressure with this engine. So we'll be, have good vacuum and it'll be street friendly. We're going to show you the parts list, including the camshaft and all the other parts that we're going to be using. And let us know what you think. So one of the important points is I have the heads and the block back from Atchison's. Lots of work was done on both of them. And I do not commit to any parts until all that is done. One of the biggest mistakes guys make building engines is they get all excited and they buy a bunch of fancy parts. And by the time you get to machining, they've stopped up on, they find out they're not the right parts and they don't need them or didn't have to buy them. And you'll find them on Facebook Marketplace all the time, guys selling things at a discount because they bought stuff they didn't need. I do not commit to any parts until all this discovery work is done and we know our calculations are accurate and we can go ahead with, with a surety that we don't have to worry about having a bunch of junk left over when the project's done that we can't use. So in this process, so this is the 454 LS7 block. Quickly, when I made the first video, I didn't even know what an LS7 was. Don't get confused with the modern LS7 style engines. This engine was 1970s. So I think what really happened is GM, when they designed this engine in probably the late 60s, LS6 was in a 1970 Chevelle. And this is kind of one step higher than that. I think GM thought these engines were going to go in Corvettes and maybe Chevelles. And they had 12.2 to 1 compression ratio, pretty crazy, radical cam. And they really thought, I think they were going to put them in Corvettes. What happened was in 1971, it was mandated that all cars sold had to be able to run on unleaded fuel, and so they could not apply them to a car. So they sold them as crate engines. So you could buy the early days of crate engines. So nowadays, of course, that's just one catalog of crate engines. There's many, and there's crate engines of every size and description that you want to buy now, but they weren't as popular back then. But this was a crate engine. The LS7 was never installed in the car. I think somebody made a comment when we made the first video. They bought one for $4,000. If you got any more for $4,000, I'm buying them because that'd be a pretty good deal. It's going to cost a lot more than that just to fix this one. So that's what happened. So Al bought his 67 Chevelle. This engine was in it. It had a 513 rear end. It was tub. It had big tires, and the guy used it to drag race, I guess. So it had been rebuilt once already, and so we had to deal with that because some of the dimensions that we were expecting weren't what we were looking for. So one of the things we have to do is project definition. Define what you're going to do, and in there you need to know what your target compression ratio is going to be and your target cranking pressure is going to be, and you kind of work back from there and you buy and assemble and use all the right parts in order to determine what they are. In this case, the engine has standard bore. The crankshaft was standard. Crankshaft is here. It's in the engine, sorry. I put the crankshaft in the engine just for purposes of this video so I can demonstrate checking deck height. And we're going to also check combustion chamber volume. So in order to determine compression ratio, you need to know your bore, your stroke, the thickness of your head gasket, your deck height, your combustion chamber volume, and your piston volume, the size of the dome on your piston, to determine your static compression. So that's going to be around 10.5. Then dynamic compression is another calculation. Dynamic compression leads you to determine what your cranking pressure. So I talk about empirical testing. All these formulas is theoretical. When you get the engine built, you put a compression gauge in and you check cranking compression, and that validates that you did it right, basically, that you achieved your goal, and we're looking for around 185 psi. So to determine that, we need the more things. We need to find the intake closing point of the intake valve, and the length of your connecting rod. And the reason for that is you're really determining where the piston is in the bore when the intake valve closes, because nothing's being compressed until that intake valve is closed. So a little bit of frustration with this one, because in the past, and I think I've probably talked about this, someone has a great calculator for determining static compression, and there's another set of calculations, one of them by Wallace, to determine dynamic compression. And you also need, because you need to know the intake closing point, someone also has another calculator to determine, if you know the advertised specs on your cam, the duration and lift and all that stuff, you plug them in and that tells you where that intake valve is going to close. So take that information, run a calculation, and you're all set. So for some reason, using those devices, not getting the answer that we want. And I still don't understand it. If anybody out there has got a clue to help me with that. I even got kind of frustrated. I watched a video a couple days ago by Richard Holderter on the exact same subject. And he's a dyno guy. He was going to dyno a bunch of different camshafts. And he talked about exactly what I'm talking about, determining static and dynamic compression, intake valve closing point, and cranking pressure. He went through the same process I just described, and at the end he said, but it didn't work. When we checked the compression on the engine, it wasn't what the calculation said. And there's my dilemma, because I did the calculation using the method I mentioned, and if I use the intake valve closing point at 50, which is 40.5 degrees on this camshaft, I get well over 200 psi of cranking compression. That's not good. We're not going to do that. If I use 78 degrees after bottom dead center, which is the advertised, based on the advertised dimensions, I get 140 psi. That's no good either. So we want 180 or 185 in that range. I always said that's kind of my target number. So what's going on? I don't know. So the way I solved it was, I went to my friend Bill Little. When I get stuck, that's my resource. And Bill ran it through his program. He has a different program. We're going to actually be pretty involved. Bill's program is Performance Trends. I think this is a subscription type program. And that's how we figured out, what we're going to do to meet our targets. So thank you, Bill, for helping me out with this. And because I was basically stuck. I didn't really know what to do next. So as a result of that, we are able to order parts. I'm going to give you a parts list. The camshaft, there it is. Everybody's interested in the camshaft we're going to use. We had a hard time finding, to get that 10.5 to 1 compression ratio. These engines originally were 12.2 to 1 compression. So what's happened is someone's rebuilt this engine before, and he did a lot of pretty nice work in it. I'm not being critical of them. But the cylinder heads are supposed to be 118 cc's. These are the 990 big block square port heads. They're supposed to be 190 cc's. And they're not. They're 119 cc's, sorry. They're 125 cc's. And I'm going to actually CC one chamber for you if you're sticking around at the end, and show you how we determine that. So if we hadn't checked that, obviously we had been disappointed with our results, because we based the calculation, I think Bill, on the sheet that I showed you, 120 or 121 cc's. So we had a tough time finding a piston. We need a 32 cc dome piston Wiseco has one. It's obviously 30 over piston. It's got 1/16 ring package, and it also has vertical gas ported vertical gas ports in it. So never used a gas ported piston before. It's a thin ring package. The cam is hydraulic roller. Of course, we're going to a roller. Howard's CL128045-09. 288, 296 advertised. 235, 243. 109 LSA. And if you watch David Vizard, LSA is really important on big blocks. If you do the calculation for all the stuff in this engine, it comes out at 108, 109 LSA. 103 centerline, 103 after top dead center centerline. So there's one of the problems. It's not a problem. The idea is to close that intake valve earlier, right, and get a head start filling the chamber. The biggest problem with making power is getting past that intake valve. So he's given the intake valve a good head start, but when it opens earlier, it also closes earlier, and that's one of the reasons that it actually closes at 40.5 at 50 thou, and that creates a lot of compression by doing that. So that's the cam, and just as after we did all this, we committed to this parts list that I'm going to show you. And this parts list is just for the short block. One thing at a time. We have time on our hands. In this case, Al's not going to drive this car till the spring. We're going to dyno it in February. So we have time on our hands, and if you got time, use it. If you got a race tomorrow, and I've been in that situation many times, you do what you got to do. But if you don't have to, take your time. Don't commit to anything until you're sure you got your numbers right. So we'll show all the other parts in the parts list. So a couple things that we need to know in order to satisfy all the conditions that Bill had to enter into his computation were deck height, and I assume the deck height was 30 thou. We're going to show you what it actually is, and combustion chamber volume. And so what happened was Mark had actually did all the work on the heads. He did really nice work. As usual, they needed more work than we thought, but they've now got all brand new valve guides, all new intake valves, I think one new exhaust valve. But someone has machined out the combustion chamber, and these are open chamber heads to start with. They're supposed to be 118, and now, so I had Mark check one while he had it at the shop. He got 125 cc. Since I got it back, I checked 3 more cylinders, and guess what? I got 125 cc. I got to check them all, and here's why. Because someone else has done this. If this was factory, 125, and maybe I check one in each head, and I'm happy that they're all going to be about the same. But someone else has been in there grinding away, and I don't know whether they measured every combustion chamber volume, or they just ground, or what they did. Because when you calculate, we're trying to get to the limit of making the most power on pump gas. If you don't use all your available compression and PSI, you're going to have less power than you could have. You've walked away, you passed on maximizing the power. If you go too far on the other side and you got too much cranking pressure, too much PSI, then you're going to have detonation. And you got 8 cylinders. You don't have to have them all detonating to ruin your engine. You only have to have one. So if there's one combustion chamber here that's, didn't get ground as much or whatever, then that's the one that's going to detonate. So I need to check every combustion chamber. That's the only way I can be confident that I'm not going to get tripped up on that, because once again, it's when the first cylinder detonates that the destruction of your engine gets started. You don't have to have them all. So we have to be sure that's all right. So one of the things I'm just going to do, because we have it mocked up, I'm going to show you determining deck height. So if Alec wants to come in here, and so we just use a deck gauge, and the first thing you got to do is make sure your piston is at top dead center. So excuse me, whoop, there you go. I already lost my position. It's okay. So I put a piston. This is the original piston, by the way. So it's actually 30 thousandths too small because the engine's been bored just from walking up. So one of the problems when you're trying to check deck height is your piston's rocking back and forth, and it makes it very tricky to determine the right amount. So I put I think about a 25 thou ribbon feeler in here. The piston's in there with no rings, and that keeps the piston from rocking back and forth. So hopefully I'll get a more accurate measurement that way. So let me try to get back to top dead center again, make sure I'm measuring top dead center. There. Okay, let's go back to there. So if that's 0, and I move my bridge off the piston, off the flat part of the piston, 30 thou, 30 or 31 thou maybe, something like that. Plus or minus the thou is among friends is okay. So I estimated that because that's typical for most Chevrolet engines as they come, so I predicted 30 thou in all my calculations. When Bill did the calculation for me, I gave him that number, and I validated it now that it is, and we're good to go. So this block has never been decked. It's got the original XCH stamp on it, and that's what actually told us that it was an LS7 block. That's the right stamp for an LS7 block. So the block has never been decked. So the pistons that we're buying, I will actually do this again with a short block. So how we're going to trim this compression ratio calculation is, I have not decked the heads yet. They're still 125 cc's. I need to get down to, based on my calculation now, 119 or 20 cc's. So you take for every 4 thou off, you take a cc off. So if you take 20 thou off, that's 5 cc's. So we're going to use that method, but I didn't let Mark mill the heads while he had them there, because that's my last opportunity to get this exactly right. So when I get the pistons are now on order. They just ordered them. Pistons back, I will assemble the short block with the new pistons and do this again to confirm that deck height is correct. Now, if we order pistons with the same compression height, it should be. But we got time, so let's wait till we get the pistons back. We'll measure it. We'll, if necessary, redo the calculation. If it's 30 thou, we're good to go. And if that's the case, then I'm taking the heads back to Mark. We'll take another 20 thou off or whatever we need to get right on the combustion chamber volume that Bill specified in this calculation, and we will be good to go. Hope that makes it a lot of information. I hope it makes sense. So that's where we're at with it. Believe it or not, the block's been painted. This is block made, cast iron paint made for cast iron engine blocks. I think it looks pretty nice. That's what we picked. And we're going to paint the heads the same. And we haven't picked out things like, valve covers and timing covers and a whole bunch of other stuff like that. Get the short block together. Make sure we don't have any issues. One thing at a time. We have time on our hands. And my mother used to say, haste makes waste, right? So we're trying to prevent that. So I guess we're at a point we can CC a combustion chamber if you're interested in watching that. If you're not, thank you for watching Gold's Garage. Please like and subscribe. We're going to try on this build to bring you as much detail as possible. And every step of it, we have time. We're going to share it with you if you're interested in following with us. So we're going to do a combustion, one cylinder combustion chamber calculation. So let me see how we can display that the best, Alex. So we have a 100 cc burette. So as you can see, and so the medium that I use is just windshield washer fluid. There's a number of different, some people use Windex. That works too. I use Windex sometime. I just don't have enough Windex to do it right now. So I'm using windshield washer fluid. So I got to fill that my burette up first of all to exactly 100. This stuff is not actually the best because it bubbles a little bit, and that you make sure you let the bubbles settle. So the problem with big block heads, if you did a small block, there's no small block that's got 100 cc's of combustion chamber volume, so you get it in one shot. What we have to do is actually empty this once, refill it again, and then see what we got. So here's the process. There's two ways of doing it. One way is you use a plate on the top, and the burette goes in the hole and it fills it. And I've done it both ways. That's the commercial plate that I actually bought and paid for. It had one hole in it. It's pretty much useless. This is the one I made out of a piece of plastic, and I drilled multiple holes because one of the problems with using the plate is sealing it and then letting the air out, and you always get air bubbles trapped somewhere. So you have to make sure that the head is level. That's why I have a level on there in both directions, and I've done that. Okay, the head is level, otherwise you're going to have flowing. You have to have a spark plug in the hole. And so I've done it both ways. I'm going to show you without the plate, just watching. Now one of the tricks is, if you're not careful, if you don't have a plate, there's a thing called meniscus. And that's the cohesion of water. Even though it's above the surface, the cohesion of water can allow the level to be actually a little bit higher than the surface of the cylinder. So you have to be careful that you watch for that. So a couple of things we have to do. The other thing we need is a little Vaseline. It's got a lot of uses. It's always handy to have some Vaseline in your shop. So we want to make sure, look at the nice job that Mark did for me on these valves. And so you want to make sure that you don't have any leakage. So I put a little bit of Vaseline on the seat and a little bit on the valve, just to help it seal. Now, pretty good chance it would seal even without it, but this makes it work a little better. There we go. And the exhaust valve the same. So seat the exhaust valve. So my first experience seeing combustion chamber was 1969 when we were preparing actually two Z28s for drag racing. So at that time I borrowed the burette from the college, so I didn't have to buy one. Now I had to buy my own this time. So excuse me, I just got to get a piece of paper here. Okay. At 100, so I'm just going to start by filling. Now you have to be careful and watch the intake and the exhaust valve, the spark plug hole. I even sealed the spark plug with Vaseline to make sure it didn't leak anything. Because if you have anything leak out, it's a pretty critical measurement. 1 cc is not very much, so you will have a bad measurement. So let's turn it on and get that first 100 in there. Let it drain there as fast as we can. And guys watching this, it'd be interesting to hear how you do it. There's different ways. There's 100. I've put 100 in it already, but obviously it's not full, so I got to put more in now, right? So I'm at 0 again. So let's go down, and so I'm going to get down level so I can watch for the meniscus and try to determine when it's full. So we're filling here. Before you get meniscus, allowing it basically to overfill the chamber is what it's going to do if you're not careful. So if I just touch there, yeah, it's just about full now. So that chamber is full. And I think we're good there. So let's come up and see what we got. There's 24, 26. I've got almost within 24.5 cc's, let's call it. So probably plus or minus a half a cc is as good as you're going to get, and plus or minus a half cc, you know, doesn't matter. It's going to not affect the performance of your engine. So thanks for watching.